In Lesson 84, we'll be learning about the multiplication of radicals and then learning some more about functions. Now in Part A on multiplication of radicals, let's just go ahead and do some practice problems. Look at practice problem A. I want you to multiply those two expressions together. And the thing you have to remember on this is that everything is a factor here. Even though we don't put a multiplication symbol, like I'm putting these red dots here, even though we usually don't put that in between a number and then the radical sign, we know that that means multiplication. So we're really saying 3 times the square root of 2 times 5 times the square root of 5. Now you know that in multiplication, the order that the factors are in does not matter. And you also know that when you multiply radicals, say you had the square root of m times the square root of n, that's the same thing as the square root of m times n, all under the radical sign or square root sign. So applying those ideas, we could go ahead and rearrange this equation, and we could make it 3 times 5 times the square root of 2 times the square root of 5. And that'll give us 3 times 5 is 15 times the square root of 2 times 5, or 15 times the square root of 10. And so that's the multiplication or the simplification of that expression. Now when you have it in that simplified form, make sure that under the radical sign that you can't factor anything out of that. And the square root of 10, there's nothing we could break that down into. There are no whole number squares of 10, so we stop there. 15 times the square root of 10. Let's do another one. 4 times the square root of 2 times 2 times the square root of 6. Now this time I won't write out quite as much information as I did on the last one. Let's just go ahead and think to ourselves that we can multiply the 4 and the 2 together, and so that would be an 8. And then we can multiply the square root of 2 and the square root of 6, which will be the square root of 2 times 6, or the square root of 12. Now think about the square root of 12. Is there something you could break that down into? Is there a factor of 12 that you know the square root of? Well, yes, there is. 4 times 3 is 12. So we could break that into 8 times the square root of 4 times the square root of 3. That square root of 4 just becomes a 2, and so we have 8 times 2 is 16 times the square root of 3. And so that would be our solution there. Always remember that. If there's something you can simplify that radical expression down into, make sure and do that. Think about it first. Don't just stop after you've done your multiplication. Check that radical sign and the expression in it to see if you can simplify it further. Let's do one more problem. On this one we'll have to expand using the distributive property. So we take 2 times the square root of 3 and multiply it by 7 times the square root of 3. And then put a plus sign and multiply 2 times the square root of 3 times 2 times the square root of 2. Now we can go ahead and simplify this. We'll have 2 times 7 is 14 times the square root of 9. Now hopefully you already know that square root of 9 is equal to 3, so let's just write 14 times 3 down. And then plus 2 times 2 is 4, and then the square root of 3 times the square root of 2 would be the square root of 6. So let's complete this. 14 times 3, that would just be 42. Plus 4. We can't simplify the square root of 6 any more than that without getting some strange decimal number. So we'll leave it like that. 42 plus 4 times the square root of 6. So a problem like that, all you have to do is expand as your first step, then go do your multiplications like we did in the previous problems. Part B of this lesson is about functions, and this is just another way to think about a function and just further your understanding of what functions are. And a function can be thought of basically like a machine, and there are lots of machines that are designed to take some material into them, process that material, and put something new out at the end. I used to work on F-16 fighter jets and design and build those, and there were machines that would just take a raw piece of aluminum, just a big block of aluminum, you put the aluminum in, and the machine would process that piece of aluminum and make a part for the airplane. So a function, it's an easier way of basically understanding a complex machine. And a lot of times those machines that take something in and put something different out, they use mathematical equations in their computer programs to make the things that they make. So understanding functions and how they work is really important. For example, here, in this function machine, we have some x values, or those are our material that we put into the machine. And so let's put a 1 into the machine, and then we perform an operation on that 1. The machine works on it, and it does 1 squared minus 1. So that would be 1 minus 1 is 0. And so we get an output of 0. That output depended on what we put in. And a machine is designed to work the same way every time. So we put a 3 in, it will perform the same operation as it did on the 1. It'll do x squared minus 1, so we'll have 3 squared is 9 minus 1, and we get an output that depends on what that input was. And then likewise for the 5, we put the 5 in, we'd have 25 minus 1 is 24, so that would be our output. So a function machine takes a value into it, processes that value, and outputs a value that is dependent on what the input was. Say this was a real machine and our values on the left were pounds of metal, and on the right those were the number of parts. So if we just put in 1 pound of metal, that wasn't enough to make any parts, so we get 0 parts out. If we put 3 pounds of metal in, we're able to make 8 parts. If we put 5 pounds of metal in, we're able to make 24 parts. Now notice something else in this machine. We put in a 1, the only thing we can get out is 0. We put in a 3, the only thing we can get out is 8. We can't get like an 8 or a 0 or a 24. For every input, there's one and only one specific output. So like we have written here, this is something to remember about how a function works. In a function, each input maps or is directed to only one output. Now all of the outputs could have the same value. For example, the 1 could map to the 8, the 3 could map to the 8, and the 5 could map to the 8, depending on what the value operation was that the function machine was doing. They could all map to the same value, but one value of the input cannot have two output or two different y values. Look at these examples that I have here of different functions with their domains and ranges. Look on the left there. If we had a domain of 2 and 4, each of those values maps to or is directed towards one and only one output in the range. That's a function. Even though they both map to the same output value, each individual input has one and only one output value. Now, look at the next one. That 1, that maps to the 1 on the right. The 2, though, it maps to a 3 and a 9. So that's not a function. That's something called a relation. But it's not a function. So try not to get those confused. The input can only have one output. For each individual input, it has one output. An input cannot have two choices for an output, two or more choices for an output. It's called a relation then. It relates to those two numbers, but it's not a function. And then the last one here, we have a 1 mapped to a 4, a 2 mapped to a 5, a 3 that doesn't map to anything. Now in a function, it has a real specific definition. Each input, it has to map or to be directed to only one output. If it's not, then it's not a function. So that example on the end there is not a function. And it's not a relation either, because 3 is not related to anything. So it's neither a function or a relation. So to be called a function, it has to, each input from the domain has to map to one and only one output. A relation, it could map to two or more outputs, but it has to have something it's related to. If it doesn't have an output that it's related to, then it wouldn't be considered a function or a relation. Let's do a couple of practice problems. I have two function examples here, or function diagrams. One of them is a function and the other one is not. Just tell me which one it is. You can just write function or not a function on there. So D, that would not be a function, right? Because that bottom number in the domain, the 9, it doesn't map to anything. So this one is not a function. I'll just say NF for not a function. It's not a relation either, right? So I'll say NR because the 9 is not related to anything. E is a function though. Each value in the domain maps to one and only one value of the range. They all map to the same value in the range, but that's okay as long as they map to one and only one value. So this one is a function, and so we'll just put an F for function there. Let's do a couple more problems. Practice problem F, I want you to tell me what the domain of practice problem D is. And so all you do is just make a set notation, and we'll just say X, 3, and 9. That would be the domain for D. That's all you have to write. And if you wanted to, you could just say that that equals capital D for domain. Now in practice problem G, I want you to tell me which of those sets of ordered pairs represent functions. Now to do a problem like this, you have got to remember the definition of a function. Every input or x value maps or is directed to one and only one value for y. So basically that means in these ordered pairs, if you see x repeated any, it's not going to be a function. So let's just go ahead and look through here. Look at number 1 there. 1, 1, 1, 3. Look, 1, it maps to a positive 1 and a positive 3 as well. And if it helps you, you can redraw, do function diagrams for these ordered pairs. If that helps you think about them a little bit better. So just look at all your x values that you have, 1, 1, and 2. So you just have 2 of them, 1 and 2. And then your y values are 1, 3, and 4. Okay, and then just go ahead and map that out. The 1 goes to a 1 and to a 3. And then the 2 goes to a 4. So you can see there that the 1 maps to 2 different numbers, but that's not a function. So we cannot say that number 1 is a function. And so why don't we just cross this one out. Number 2, look at that one. 2, 3, 3, 5, and 1, 5. And just think about it. As long as each input maps to a different output, then it's a function, or maps to one and only one output, it's a function. And usually what that means in an ordered pair set like this is if x is not repeated, then it's a function. X is not repeated. We have a 2, a 3, and a 1 for our x values. So this is a function. So we'll just go ahead and circle that one. That is representing a function. Each input value maps to one and only one output value. Now the 3 and the 1, they both map to a 5, but that's okay, right? That's just like practice problem E up there. The same number, or they map to the same number, but they map to one and only one number. There's no x value that maps to 2 different y values like we had in 1 of practice problem G. Now let's go ahead and look at 3. We have 4, 7, 1, 9, and 4, 2. Well, right away we see we have 4, an x value repeated twice, so that should tell us right away that that is not going to be a function. The 4 maps to a 7 and to a 2. That's not in the definition of a function. In a function, each input maps to only one output. So the set of ordered pairs in 2, that was the only set out of those 3 that was a function. Okay, well that's all for lesson 84.